All right, you guys, let's go over this warm up here.
So, think about it. This is a function we can find, and this is a function we can find. Not that different.
Okay. So, let's look at this scenario here. Why is that area between those two curves positive?
So you can't have negative area?
Why not? We can.
Without having negative numbers.
But we can have negative area. The area under the curve is often negative. Yeah. Like if I was doing this, the integral of this curve would be like a minus b plus c. So that would be negative area if it's underneath.
But b isn't negative. It's just you're subtracting it because it's.
If I do the integral, I'm going to get negative b as an answer. We will never get a negative number when we do the area between two curves. But we can get negative when we do the area under one curve. Kat, what do you got?
Is it like the second curve, the bottom curve, is kind of like the x-axis acts when you're doing the regular curve, as it sets like a bottom line for you. So if you were to go under it, like if you were to continue it, you might get negatives over here. That's it, like alternating with it. But it's just like, you know, the area between two things, like the area between, you know, the curve and the x-axis is all
Let's just think about number one here. Why is that giving us a positive number? They're both above the x-axis, okay, but I can still subtract two positive numbers to get a negative number, right? 3 minus 10 is negative 7.
You always subtract the bottom. So when it's positive, the bottom is always going to be less than the top. And then when it's negative, you're subtracting the negative.
Okay. Yeah. So let's do these one at a time, but yes, you got it. So we have a big positive area here. This is the integral of f of x. The integral of g of x is this, which is a positive area, but it's smaller than the blue area, right? So when we take that away, we subtract it, we're left with still a positive amount. So that's what's happening in this one. We have a big positive area minus a smaller positive area. And so that's going to be greater than 0. Okay. Number 2, yeah, David, keep cooking.
The top one's positive. The small one, the bottom one, is negative, so just subtract it.
Yeah, so we have a positive area minus a negative area. And so that's going to be greater than 0. Yeah. Okay, and then the third one, what's going on here? Leon?
The top one is less negative than the bottom. So when you add g of x, since you're subtracting the negative, g of x is going to take it past the x-axis because it's from 0, so it'll be a larger positive number than x is negative.
Yes.
That's confusing.
Yeah, but you got it. Yeah, so this is the integral of f of x. And so that's a negative area. But then we're subtracting a more negative, larger magnitude. Yeah. So we have a small negative area minus a large negative area. Yep. So we'll always get a positive number when we do top minus bottom. Does that make sense? Good. All right, let's look at these geometry problems. So for number 2, we're doing pi r squared h. So volume equals pi, what's r? 5, so 5 squared times h is 20. All right, so 25 times 20 is something. 500. So 500 pi. Nice. Okay, number 3, how do we have to do this? Yeah,
Take the volume of the larger cylinder and subtract the volume of the smaller cylinder from it.
yeah. Okay, so we have like pi r squared h minus pi r squared h. Do you agree? Okay. For the purposes of today's lesson, so the reason I'm doing this is because we're doing volumes today, and they're going to look, our volumes are going to look like this. Is this chill if I take out pi and h and call this like r squared minus r squared? Is that cool?
Yes.
Everybody cool with that? Sweet. What's big R? 4. What's little r? 2. Yeah. So we have 16 minus 4, so 12. Pi 20 times 12, which is 240 pi. Okay, cool. We're gonna do some volumes today, like I said. When in terms of volumes, H, I'm gonna try and make this connection before doing notes on it. We'll see how it goes. H is gonna be like the integral part of the volume. We're gonna get that number from doing the integral. The R, we're gonna get from the functions that are involved. Pi is pi. We're just gonna use pi. So same thing with this. That is gonna be the function. H is gonna be the integral. It's gonna be the integral / it's gonna be the bounds of integration. Let me say that as well. But really, like, what we're doing today is just finding the volume of cylinders, except the cylinders change size as we go along. So like maybe our cylinder looks like this instead. It's like a growing kind of shape here. Yeah, it's cool. It's cool. These notes are gonna make you look really smart. When you're doing these math problems, you know, you just like let a piece of paper fall out of your binder, like, oh, whoa, sorry, like, forgot my calculus notes, you know. You're gonna look really smart. Okay. Oh, yes, I have a Desmos for this.
Oh, she does.
Revolving a curve around the axis with sometimes there's a little cylinder in the middle. But let's take a look here. Oh, wait a minute. Oh, you guys, thanks for going on that journey with me. All right, how does this thing work again? All right, so. Whoa. Oh, okay, here we go. So here's our curve. It's square root of x, right? Let's see. Move axis of revolution. Yeah, so we're gonna rotate this around the x axis. Let's just reset everything. Yeah. And basically what's happening is we're revolving this curve, and so like here's like a section of it revolved around, and you see it makes this kind of solid shape. Prepare to revolve another. I want to see all the. Maybe this is it. Prepare to revolve another. I don't remember this. I might just have to. No, that's not helpful. Oh, here we go. Here, this is the slide I wanted. Okay, look. So there's the area. If we're going from A to B, let's just revolve this whole curve here. From A to B. Boom. Here's what we're doing. We're revolving, nope, reset. We're gonna revolve this around just the x-axis. Revolve. So what we're doing is we're creating a solid shape like that. That's growing. This is kind of like the thing I just sketched. And it's basically cylindrical in its properties in the sense that it's like a circular solid. But notice like it's changing and growing as we go along. So we're gonna find the volume of that. And it's made up of these like little circles, you know? And so it represents basically a cylinder that the radius is changing as we go along. Sometimes we'll just revolve part of that. And so we'll get a solid that looks like this. And then sometimes we'll revolve this around, where's my axis of revolution? There it is. Another line. And so what happens is basically we have this function here, this kind of solid with like something missing in the middle. Like in this case, a cylinder shaped thing is missing in the middle. And this is like our r squared minus r squared kind of deal, which looks like this. So it's going to be a volume that's more like this third one here. So sometimes it's hard to draw these well. Sometimes this axis of revolution will be in different places, and that's going to be the challenge, is trying to figure out exactly what it is that we're supposed to be integrating. Because you see, if we revolve it above there, now it's, you know, it's different. It's kind of a different volume. It's kind of cool looking. Don't you agree? It's cool looking. Yeah. Or sometimes we can get crazy. Where's my axis of revolution? Like partially inside there. I don't know. This is gonna be wild. Whoa. Oh, this looks like a cylinder, but it's not. And then sometimes we're gonna be going around the y-axis. So it's all basically the same thing, but that's kind of what it looks like. Okay, now we can visualize it. So let's do it. Here's how it works. A lot of these formulas are already written on there. So there's basically two methods. The disk formula. Disk refers to there's no gap in the middle. It's completely solid. And our formulas are right there. So it's pi r squared dx if we're going around the x-axis, pi r squared dy if we're going on the y-axis, and r just represents the function. Because this is the distance between the solid and the x-axis. It's just that right there, whatever our function is. But so it's pretty simple. Let's say that this is a graph of, let's see, like square root of x, because it looks like it could kind of be. Let's just pretend. And let's say, you know, we're integrating from a to b, whatever they are. We just integrate pi a to b square root of x, because that's our function, squared. And basically this is our pi r squared h. And usually we'll just have a calculator for this, so it's pretty straightforward. So r comes from the function, h comes from integrating from a to b. That's it. You don't need to know the difference between disk and washer, like in terms of the words, the names. What you need to recognize is when a shape is totally solid, it's just pi r squared. And when a shape is not solid, like there's something missing, we have this formula instead. That's the difference that you need to pay attention to. Now this is called a washer formula because they're kind of like washer shaped. Not kind of washer shaped, they are washer shaped. So r represents the outside radius, or we would say like the outside, maybe we'll say the outermost function. And r, little r, the inside radius, which is the innermost function. And when we say innermost and outermost, these are all like relative to the axis of revolution. So sometimes it's above the function, and so the outermost one is like the bottom function. Sometimes their axis of revolution is below. We'll look at some different examples here. Here's another way to tell the difference here. This is something I just thought of. So not solid, there's a gap in the middle. The solid is not touching the axis of revolution. Whereas our disk method, it's completely solid. The solid is touching the axis of revolution. Just another way to distinguish. It's very straightforward if you're able to keep these two things straight. If you're able to tell the difference. And then sometimes it's challenging to figure out what exactly the big R and little r should be. And that's what we're going to be looking at when we do some examples. Let's go to the next page and do some examples. You'll need a calculator for this. Actually, we'll just set up these integrals because that's the harder part. So we'll do some stuff with the calculator, but not very much. But but you will need it for your homework. Okay, so we're going to take this region, which we can sketch a graph of that. So here's y equals 2x, y equals 0, x equals 3, and so we're talking about this solid right there. So we're going to revolve this region around a few different lines to see how it looks different. So if we're revolving it here around the x-axis, so that's our axis of revolution. Turn to your neighbor. Is this going to be a solid shape, or is this going to be one with a gap in the middle?
It's gonna be a solid shape.
Telling Caleb.
Okay, yeah, you guys got it. It's going to be solid. We can see here that the shaded area is touching the axis of revolution. So it's just going to be one big solid shape. It's going to kind of look like this here. And it's going to, be circular when we revolve it, but that's sort of what we're working with. And so what we need is we need the integral from a to b of r squared dx. We just have one radius because we're dealing with a solid shape. What is that radius? It's not 6.
2x?
It's 2x. So it is 6 at the very end, but it changes along the way because it's a function that's growing. So our radius is 2x. That 2x will always give us the distance from the axis of revolution to the outermost curve. And so when we integrate this, it's just pi times the integral from 0 to 3 of 2x squared dx. Or, 4x squared if we want to distribute that. That's fine. This is one that we could do by hand. We just usually won't. We'll just usually have a calculator. So, yeah, I want to focus more on the setup here. So let's look at letter B. Same region. And now we're revolving around the line y equals 6. So turn to your neighbor. Where will that be relative to that shaded region?
At the top of it.
Yes. So yeah, if we plug in 3 for x, like the height is 6, so y equals 6 is right there. Okay, so that's our axis of revolution. Wait, I forgot. I have an iPad, so I can do this. Haha. Make it nice and straight. There's our axis of revolution. So when we revolve this solid, like upwards, turn your neighbor. Is this going to be solid, or is there going to be a gap? Disc or washer?
I think it's because it's touching. Yeah.
Okay, so here's what it's going to look like once we revolve it. So, do you guys see that big old gap in the middle? I do too. So, just because it's touching at one point, what we're looking for the disk method is the entire shaded region is on the axis of revolution. So here's the axis of revolution, our blue line right there. Our red shaded region is not touching the axis of revolution. So that means the formula that we're using here is pi a to b r squared minus r squared. So turn to your neighbor. What do you think those two radii are? This is the hardest part sometimes, figuring out the radii. Talk about it. Okay, this can get a little tricky. So we have our axis of revolution. What is the outermost radius? What do you guys think? 6. It is 6. Just the number 6. If we look, here's the edge of the solid. It's always 6 away, whether we go up or down. So our big radius is just regular 6. Okay. Our inner radius, 6 minus 2x is exactly right. It's this distance right here. And so it's our line y equals 6, subtracting 2x. So once we can identify the radii, we just plug it into the formula. So it's just pi 0 to 3, 6 squared minus 6 minus 2x squared dx. All of that should be in parentheses there because it's like all in one integral. And as you're doing this on the calculator, you would want to just type it in exactly like it appears right there. There's not a need to FOIL it out. There's not a need to do arithmetic that the calculator can do. Just pop it in there and it's going to work. Questions on why those are the two radii? Okay. You guys try the next one. It's going to be similar. Outer radius is 8. Yes. That's a constant distance because that bottom part there is just horizontal. We're going to see some stuff where there's two curves involved. This is just horizontal distance. Inner radius, 8 minus 2x. Yep, so this is basically identical to the last one. Cool. Questions on that one? All right. So letter D. We're going to go around the y-axis. But it's the same region. So it's here. Now we're going around vertical axis here. Turn your neighbor. What's that going to look like? How do we do that? What do you think? Okay, what are you guys thinking for the bounds of integration here? What are we integrating from? -3 to 3.
Oh, no.
So we're going this way. This is what it's looking like. Oop.
0 to 6.
0 to 6. Yeah. Because that's where our solid goes. So it's kind of spinning sideways. Is this disc or washer? Washer, yeah, because we got a big old gap there. And if you want, you can say it washer, because that's fun to say. So what's the outer radius going to be? 3, yes. The outer radius is 3. That distance is always the same. It's a straight vertical line there. Okay. Inner radius, 1/2 y is exactly right. Okay. So this one we have to look at it from a sideways point of view. This line here is y equals 2x. When we look at it from y's point of view, it's x equals y over 2 or 1/2 y. And notice the distance between the axis of revolution and the curve is like the coordinates of the curve itself. So we don't need to do 3 minus y over 2. It's just y over 2. Because it's going from the axis to the function. So we do 3 squared minus y over 2 squared dy. In the calculator, we would just use x instead of y. And it would give us the right answer. It wouldn't graph the same function. It wouldn't look the same. But it would be the equivalent function but sideways. Questions on that one? Okay, y'all do E and F.
So I think This one here, E is just the other line is like this. Oh shit. You're right.
Yeah, I did a little sketch up here so you can visualize it. Take a couple more minutes. Both of these are going to be, in terms of y though, they're going to be some integral something 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 dy, because since we're revolving around a vertical line, that means we're integrating vertically. We're integrating in terms of y. When we integrate from like left to right, we revolve around a horizontal line, that's going to be like dx. So we do want to be thinking about the function y over 2 instead of y equals 2x. And our other things. Okay, let's talk about these here. Is one of these disk? Is it solid? Which one? E. Okay, and so F is not solid. Yeah, there's a gap in there. Okay, so we know this is going to be pi r squared dy, I guess, a to b. This is going to be pi r squared minus r squared dy from a to b. Okay, so what's our radius in E? Who thinks they've got it? So 3 minus y over 2. Agree, disagree, what do we think? I'm getting 2 thumbs ups, 3 thumbs ups. Thumbs up or thumb ups? What's the plural of thumbs up? Thumb up. Thumbs up, right? Gotta be thumbs up. Okay, this is correct. Here's our radius, it's right there. So y over 2 would give us this radius. That's not what we want. We want 3 and then subtract that radius right there. Okay, so this is just going to be the integral pi times the integral. It's really easy to forget pi, by the way, so just don't. From what to what? 0 to 6, yeah, because we're doing it in terms of y. And so it's just 3 minus y over 2, or 1/2 y squared dy. Okay, in letter F, what's our outer radius? 4 minus y over 2. Yep, 4 minus y over 2. So there's our axis of revolution. Our outer radius is there. So anytime you need to find the distance between two things, like subtract them. So our axis of revolution is 4. Our curve that's on the outermost function is y over 2, so it's 4 minus y over 2. In letter D, the axis of revolution is 0. So that's why this inner radius here is just 1/2 y or y over 2. It's not like 3 minus y over 2. What's our inner radius? 1. Yep. Nice. So we're still integrating 0 to 6. 4 minus y over 2 squared minus 1 squared. Obviously 1 squared is 1, so you can just write 1. But and again, like if we needed to, we could do this by hand. We would FOIL that out, we would combine like terms, we would use reverse power rule, we'd plug in the bounds, subtract, and then whatever that number is times pi. We could do it. You will so rarely have to do it that we're basically just only going to do it on the calculator. Or really, we're just like talking about setting it up right now because that's actually the more difficult part. Okay, any questions? We'll do another set of examples after this. Okay, so let's go to its example 4, 5, 6. Example 6. So there's several other examples in there that you guys can practice with. So now we're going to use two curves, y equals x squared and y equals cube root x. I want you to see if you guys can figure out what that region looks like without using a calculator first. Just do a little thinking here. See if you can sketch that. All right, yeah, a lot of you guys got this. So cube root x is going to come here and go like that. And so the region we're talking about is this region right there. What is the x coordinate where they intersect? 1. Yep. And the y coordinate there is 1. Yep. Okay. This is usually what we're going to be working with. Two curves revolved around the x-axis, around the y-axis. Let's see if I can draw that a little better. Look a little more like that. There we go. Okay. So turn your neighbor. How do we set that up for rotating around the x-axis? What does that look like? Talk about it. All right, so yes, this is washer method. Our outer radius is that. What did you guys say for the outer radius? Cube root x is correct. Yep. It's just the distance from 0 to cube root x, which is just cube root x. What is our inner radius would be this, which is what? X squared, just x squared. Because our axis of revolution is here, the distance from the axis of revolution to the function, that's what we're looking for. If the axis is 0, it's just whatever the function is. So our volume then, we're going to integrate pi 0 to 1 cube root x squared minus x squared squared. Okay. You guys do B and C. let's check these. So, letter B. What is our outer radius going to be? Square root of y. Yes. Okay, so it is the x squared function. That's our outer radius. But we need it to be in terms of y because we're integrating vertically. What's our inner radius going to be? Y cubed. Yep. And so then when we integrate, it's pi, and we're integrating from where to where? 0 to 1. Yep. So that doesn't change because both intersections are 1. They intersect at the point 1, 1. So this is just root y squared minus y cubed squared. Of course, we could say this is the same as y minus y to the 6th, but we don't need to. Okay, questions on that one? Okay, letter C, we're back to a horizontal line, so these, we do want to use the functions in terms of x. What is our outer radius going to be? 1 minus x squared. Yes. Our axis of revolution is 1. The distance between 1 and x squared is 1 minus x squared. What is our inner radius going to be? What's it? 1 minus cube root of x. That's right. So anytime, here's the short way to remember it. Anytime we're revolving around x equals 0 or y equals 0, the radii are just going to be the functions themselves. If we're revolving around some other number like y equals 1, y equals 2, it's just going to be 1 minus the function. 1 minus the function for both of the radii. Okay. So that's basically it. The hardest thing is figuring out what the radii should be. Once you get the hang of it, it's not that bad. It's just whatever the line is minus the function usually. You have to identify which one's inside and outside. Sometimes that is tricky because you have to be able to visualize which direction you're revolving in. Once you get the hang of it, it is very straightforward. So the key really is just practice. So I'm going to give you guys some time to work on your delta math because you'll see some more complex curves and actually get some practice with your calculator. So we'll take some time to do that. Let me know if you get stuck or have questions.